the screen. So welcome everybody. Well, as you saw, if you had joined a little bit earlier, there are two presentations today. So we will start with Minhaeng Cho, and I think see the title changed again.
Slightly. I'm sorry. Yeah,
It's
it's kind
okay.
of evolving, right?
It's perfectly fine. Yeah. So we will have um, half an hour talk and 15 minutes for questions, and then please just write if you in the chat if you have a question in the end, and we will make you panelists so you can ask the question live. So Min will tell us about infrared and visible spectroscopy of n-dimensional material, and well, Min, floor is yours.
Yeah, thank you, Maxim and Thomas, for inviting me. This is a wonderful opportunity for me to discuss these new, interesting, and very exciting works that we have been studying over the past 3 years. And what table of contents? I'm going to talk about 4 different systems: zero-dimensional colloidal quantum dots and one-dimensional golden hour particles and graphene multilayers. And the last topic is just a mundane solution system, but essentially we have been trying to develop a new technique for the two-dimensional electronic spectroscopy with more than one lasers. So that is another very exciting work that is currently under investigation in our laboratory. So the very first topic is quasi zero-dimensional colloidal quantum dots. And probably I don't have to explain what semiconducting nanocrystals are, but essentially you can control the size of small quantum dots, which results in the change in the band gap transition energy. So if you increase the size of quantum dot, then you will be able to reduce or lower the band gap transition frequency. But the question is, can we make quantum dots with the band gaps in the mid-IR region? That is the question we had. And in principle, it is possible because you can make this quantum dot very, very large so that the band gap transition frequency falls into the mid-IR region. But that is not always good, because if the size of particle is very large, then apparently there is this disadvantage that you cannot achieve very high quantum dot density. That means that the material itself is not very useful for real applications. So people have been trying to find an alternative way to achieve this kind of synthesis of quantum dots that absorbs and sometimes emits photons in the infrared range. And this is the technique they sort of invented, self-doping method. So this is the conventional and traditional quantum dots exhibiting the band gap transition from 1sh to 1se state, and of which frequency is in the visible domain. But if this 1se state is filled with 2 electrons, then suddenly this colloidal quantum dot, whose size is still very small, maybe 2, 3, 4 nanometers in diameter, but still this kind of quantum dot can absorb infrared light that is associated with the transition from 1se to 1pe state. And this is the FTIR spectrum of these self-doped colloidal quantum dots. And look at the x-axis here, the wave numbers. That is perfectly in the mid-IR range. So this is the technique that Professor Chong in my department used to synthesize this kind of colloidal quantum dots. And once you have this infrared intraband transition colloidal quantum dot with mid-IR absorption and mid-IR photoluminescence property, they could be very exciting applications like tunable mid-IR laser, tunable mid-IR detector, and also these particles can be used for photothermal imaging with infrared and visible beam. And also the frequency range, 3 to 5 microns and 8 to 10 microns, that's perfect for the atmospheric communication. And also these particles can be used as mid-IR filters, sensors, nonlinear optical materials, and so on. So once you have these colloidal quantum dots in the infrared domain, there are many interesting possibilities in the future. But still, we have very little understanding about the relaxation processes of the excitons and biexcitons created inside this colloidal quantum dot. This is the structure, very schematic representation of the colloidal quantum dot. And the passivation layer is either DDT or olelamin. And this is the energy level structure. Typically, this is the valence band, and this is the conduction band. And obviously, valence band is completely filled with multiple pairs of electrons. But this self-doped mercury sulfide colloidal quantum dot has 2 electrons. They occupy 1s state, so that this electronic transition is allowed, and of which frequency is somewhere around 2500 wave number. And this is the ab initio calculation results of these molecular orbitals, 1s-H state and 1s-E state. Well, this is not perfect sphere, but quasi-spherical symmetry. Therefore, the 1s-H and 1s-E orbital looks like a 1s orbital of hydrogen-like atom, more or less spherically distributed. But the distinctive difference between 1s-H and 1s-E orbital is the spatial delocalization. 1s-E state, electrons are preferentially delocalized on the surface of this colloidal quantum dot. And you can see the 1p state, they look like a p orbital of a hydrogen atom. That's good. So the transition from 1s-E to 1pe state is allowed, so that the Fermi level is lifted up somewhere there, right? And this is ab initio calculations of this very large system. This is not an easy, cheap calculation, very expensive calculation, which was performed by Dr. Kim at Kyoto University. And I just skipped this slide, but I just want to show that the electron distributions is really, really surface delocalized. And this is the FDIR spectra of this colloidal quantum dot with the DDT ligand and olelamin ligand. And this, look at this dashed blue curve. That's the FDIR spectrum. All these sharp features, they are just either ligand or solvent. Solvent in this particular case is tetrachloroethane. So you just ignore these sharp features. Our laser spectrum sits right there in between these complicated solvent band. So we can excite the quantum dot selectively. But well, this is the pump probe data. And we changed the pump intensity from 56 microjoule per square centimeter up to 750 microjoule per square centimeter. And this is the isotropic pump probe signal. And they all fit with the tri-exponential function almost perfectly. And that's good. But there are many puzzles, actually. As pump power increases, the relative amplitude of the fastest component, whose time constant is just about 1 picosecond, that is awfully fast. Actually, we didn't expect this fast component contributes to the pump probe signal. But anyway, we observe this fast component. There is another intermediate component of which time constant is about 10 to 20 picosecond. There is a very slow component whose time constant is around 300, 400 picosecond. And what is really puzzling is that the relative amplitude of these 3 components do depend on the pump energy. As the pump energy increases from 0 to up to 700, 800 microjoule per square centimeter, the fast component gains its amplitude. On the other hand, 2 components show decreasing pattern with the pump energy density. So this was the puzzle that bothered us for a long time. It took a long time to figure out and rationalize all these experimental data. And we finally came up with this kind of complicated kinetic scheme. But the more important thing is this. There are at least three different distinctively noticeable relaxation pathways. The first one is the intraband Auger process. That means one exciton is annihilated and its excess energy is transferred to the electron here, so that this electron goes up somewhere in the high excited state. That is what is called Auger process. But this is the first time we observed intra-band Auger process, and that has to take place in the time scale of 1 picosecond. And there are two different relaxation mechanisms like inter-sublevel transition and exciton ligand vibrational energy transfer, of which time scale is longer than 500 picoseconds. So this is the overall kinetic scheme mechanism. And we solved this rate equation numerically, and we could simulate the entire isotropic pump-to-probe signal. And the simulated results appear to be really in good and excellent quantitative agreement with the experimental data. So as what is happening is this, as you increase the pump energy density, you can create more and more bi-exciton states. That is what is happening. And this bi-exciton state quickly relaxes back to the one exciton state through this intraband Auger process. So that was the main and the principal observation from this work. And this is the summary slide. I skipped this because at the end of my talk, I will show you the overall summary. So I'm going to give you the summary of this part later in my talk. The second topic is the quantum wire. I shouldn't say wire, it's just a small quantum nanorod. And the system that we studied is this silica-coated golden nanorod. Aspect ratio is about 4. So the length is about 40 nanometer and width is 10 nanometer. And this is the absorption spectrum. The lowest absorption band corresponds to the longitudinal surface plasmonic resonance. So this surface plasmonic resonance is a well-known phenomenon. I probably don't have to explain it in detail. But essentially, the quasi-electrons inside this gold nanorod would dance together with the electric field. Applied electric field will move up and down. Here in this case, positive, negative electric field. So that the quasi-electrons will coherently oscillate following the electric field amplitude due to the Lorentz force. This is nothing but the minimal coupling Hamiltonian. So this electron dancing or surface plasmon will sustain for a while until the electric field is present. But we are using very short pulse, femtosecond laser pulse. So after this pulse is gone, what is happening is electrons collide with each other or scatter with each other. That induces a heating process. So there are multiple relaxation mechanisms. The first one is the electron-electron scattering induced the heating effect, whose time scale is not clearly determined yet, but presumably it is completed within 100 or 200 femtosecond. And the electron-phonon coupling or electron-phonon relaxation takes place in the time scale of tens of picosecond. The phonon-phonon coupling, which is nothing but the heat dissipation from the golden nanorod to the bed, that takes place very slow time scale, 100 picosecond or 200 picosecond, sometimes even longer. But the key question is this: can we actually directly observe this kind of electron-electron heating process or electron-electron scattering process using the femtosecond two-dimensional electronic spectroscopy technique? That was the question that we wanted to address. And indeed, that is possible. But before that, this is the pump-to-probe signal. What is happening when the golden nanorod interacts with the pump beam? What is happening is the following. Simply the absorption spectrum undergoes a redshift like this, and then the spectrum is broadened, so that the transient absorption spectrum, which is nothing but the difference between this blue curve and black curve, that shows this kind of dispersive shape, positive signal, negative signal. That is what we measured actually using the femtosecond laser pulse. But the absorption band, the longitudinal SPR band, is exceptionally broad because of the heterogeneity. However, our pulse spectrum is not that broad, but that is good because we can selectively excite sub-ensemble of golden nanorods within the broad heterogeneous distribution. So this is the series of pump probe spectra with the center wavelengths to be 720 nanometer up to 800 nanometer. And this is the pump probe time profile. You can easily see the slowly oscillating component. Look at the time scale of this x-axis, 0 to 300 picoseconds. So this oscillation is definitely not a simple molecular vibration at all. This is something to do with this kind of extensional motion of this golden nanorod, of which frequency is somewhere close to, the period is close to 50 picosecond, very slow component. And this slow extensional vibrational feature also can be seen in the nodal line here. You see the oscillating feature, right? And we could fit the entire pump probe spectrum using 3 exponential function, 2 exponentially decaying function, and the other one is a damped sinusoidal function. We could determine all these amplitudes and decay constants, and these are the decay constants. I'll just skip this slide. But because the more interesting observation was made with the 2-dimensional electronic spectroscopy setup like this, using a partial shaper dazzler here. I don't have to explain the working principle of this 2-dimensional electronic spectroscopy technique with the partial shaper, right? But anyway, one thing that I like to emphasize is we needed to use these polarizers to get rid of very strong scattering signal, because the size of the particle is a few nanometers, even larger than that. So there has to be a larger contribution from the scattering, unwanted scattering. We could get rid of most of the scattering contamination using these polarizers. So this is the 2-dimensional spectra. They look more or less boring to some extent because absorption band is very broad, and these are the 2-dimensional electronic spectra. And this is sort of a superposed spectra of a series of 2-dimensional spectra. And particularly, we extracted the nodal line slope from a series of 2-dimensional spectra with changing the center wavelengths. And these dots in this figure, that's the nodal line slope. And this actually gives us direct information about the size heterogeneity. So of course, you can measure the TEM image to estimate the heterogeneous distribution of this golden nanorod. But this is another very expensive way to estimate the heterogeneity of this golden nanorod. But the more interesting thing is this. So the time resolved 2-dimensional electronic spectra gave us the nodal line slope. Look at these black dots. That's the experimental data. But you have to ignore the short time part because that's when the pulses are all overlap with each other. So there could be all kinds of scattering and coherent artifact and so on. So you just have to ignore the short time part. But from 150 femtosecond to maybe 300 femtosecond, we could see this kind of transient rising pattern of the nodal line slope, and then followed by a slow decay. And this slow decay is nothing but the homogeneous electron phonon in this dephasing time constant. I like to emphasize the word homogeneous because we are carrying out this 2-dimensional electronic spectroscopy experiment in a photon echo geometry. Naturally, we do not have any problem from the size heterogeneity. So this number is really homogeneous dephasing constant. But the more important thing is this initial rise of the nodal line slope. And this, we believe, corresponds to the electron heating effect. You still remember the question that I wanted to address from the beginning of this project, right? So we were able to determine and directly observe the electron-electron scattering processes using this femtosecond two-dimensional electronic spectroscopy technique. Okay, I'll just skip this. And this is the summary of the second part of my talk. The third part, well, this is again very different type of experiment. We studied graphene, but not graphene itself. We studied water structure on the surface of graphene. So the overall system looks like this. So there is a substrate down here. This is the substrate. And in this particular case, we use the calcium fluoride. And then we put a monolayer of graphene or bilayer and so on. The graphene multi-layer is on top of this substrate. And then we could put a droplet of water. And the conventional way to study the surface property is this water contact angle measurement technique. This is a relatively simple technique, but I like to emphasize that this is a macroscopic technique. What I mean by that is this does not provide you what is happening precisely at the interface between water and this graphene surface. So we had to use molecular spectroscopy. Obviously, the very good technique for a suitable technique for this particular problem is the vibrational some frequency generation technique. But before that, there is an interesting controversial issue here, and several groups of people published a series of papers sometime around 2012, 2013, and so on. They have been debating about this issue for quite a while, and still this issue has not been completely resolved yet. So one group of people emphasized that graphene monolayer is basically transparent because it is very thin layer, atomically thin, so that the substrate under the monolayer of graphene can directly interact with the water up there. And they used the WCA, water contact angle measurement technique, to support their claim. But the other group carried out exactly the same measurement, but their conclusion is completely opposite. It is not transparent, it is translucent, and sometimes completely opaque, even with a single graphene layer. So this is all very confusing, and they were sort of in intense debate about this issue. And that is why I think it is very important to study this problem with the molecular spectroscopy, like vibrational some frequency generation technique. I probably don't have to explain this, the principle of this technique at all, right? Basically, we measure the some frequency generation signal. And the target mode is water OH stretch mode. And here I'm talking about normal water, not heavy water or isotopically diluted water, just the normal H2O. And this yellow curve, that is the water OH vibrational some frequency generation spectrum on top of bare calcium fluoride without any graphene monolayer. So if I put one layer of graphene, that's this purple, suddenly the SFG spectrum intensity increases dramatically from here to up there. So this indicates the graphene monolayer, just a single monolayer of its thickness is just about, 2-3 angstrom. But still, this single graphene layer induces very strong ordering of the water structure at the interface between graphene monolayer and water. But the more interesting observation is this. If you increase the number of graphene layer from 1 to 6, you can see gradual change of the some frequency generation spectrum, not just in the low frequency domain. Look at this high frequency domain at around 3600 wave number. That suddenly appears right after when the number of graphene layer is larger than or comparable or equal to 4. So we could easily assign this peak to be the dangling OH. Well, actually, it is not free OH. It is OH groups pointing toward the graphene layer. And we could assign all these different bands, and basically the entire spectrum can be fit with the 3 Lorentzian function. Their center wave numbers are 3200, 3400, and 3600 wave number. The lowest component, 3200 wave number component, that is either strongly H-bonded water or the surface water that is basically produced by the intramolecular vibrational coupling between the 2 OH groups. So the clear assignment of these 2 bands is not very clear, but the more important thing is the observation of this 3600 wave number that can be easily assigned to the non-hydrogen bonded water. Here, what I mean by this non-hydrogen bonded water means these water molecules do not have, these OH groups do not have hydrogen bonding interaction with another water molecule. And these components do change with respect to the number of layers. 3200 wave number component has its amplitude decreases upon increasing the number of graphene layer. On the other hand, the dangling OH group 3600 wave number, its intensity increases as the number of graphene layers is larger than 4. So this indicates that the water ordering or dramatic change of the water interfacial water structure when the number of graphene layer increases from 1 to 6. And once the number of graphene layer is larger than 4, 5, then there is no difference. Basically, the graphene multi-layers behave like a hydrophobic surface to water. So that is the main conclusion of this work. And the final topic is yet another subject, and well, the system is bulk solution. But we wanted to develop a new two-dimensional electronic spectroscopy technique with 2 modular lasers. But before that, I'd like to just give you brief background introduction about the two-dimensional spectroscopy. You need to have at least 3, 4 laser pulses, right? So the first 2 pulses during this time tau, the molecular system is in a superposition state like that. And because this is a non-stationary state, so any expectation value you can calculate from this non-stationary state would be changing in time. And indeed, it oscillates with the frequency of transition frequency between the ground and electronically excited state. And again, the second coherence time, t, the system is again go back to the another superposition state, and its expectation value also oscillates. And this is basically the Hertzian dipole emitting the photon echo or any kind of 4-wave mixing signal. But during t, the system is either on the electronically excited state or ground state, and that is important to keep in your mind. And this is the conventional 2-dimensional spectroscopy technique, very simplified and schematic representation of 2-dimensional spectroscopy. You have a single laser, typically amplified modular lasers. Using 1 or 2 or multiple beam splitters, basically you can carry out nonlinear spectroscopy. Here, there is this black box, and what is that black box? Is this complicated optics. The conventional method utilizes multiple translational stages, but you can use pulse shaper or combination of pulse shaper and translational stage to essentially control the delay times, 3 delay times or 2 delay times, depending on the detection method you're using. Now the question is this: can we replace this entire experimental setup, laser, with the two lasers? And if these two lasers are not synchronized, if these two lasers are completely independent, you will see no interference pattern on the screen, right? So the interference term is gone. Here, I like to emphasize that the interference term is gone when you take the average interferogram over multiple interferograms, right? Because you have to average over the phase factor theta here, and this integration, that's nothing but the averaging, will kill the interference term. So you don't see any interference pattern, and that means that you cannot do the coherent spectroscopic measurement with just the two independent lasers putting onto your optical table. But if these two lasers are sort of phase locked using the synchronization technique, or referenced to the atomic clock frequency, so that you can stabilize the repetition frequency of these two lasers. At the same time, if you can stabilize the carrier envelope offset frequency simultaneously, then these two lasers become completely coherent with each other, so that you can do all kinds of coherent nonlinear or linear spectroscopic measurement. And this is the simple linear spectroscopic measurement using two frequency stabilized optical frequency comb lasers. And this is the two lasers. They have a slightly different repetition frequencies. The upper one has FR plus delta FR, whereas the lower laser has the repetition frequency of FR, so that there is a continuously changing time mismatch. And this delta T could be controlled easily by controlling the detuning frequency delta FR. This is the experimentally controllable factor. So once you can control and set to be 1 Hertz, whereas the repetition frequency is 100 megahertz, then the time delay, the minimal time delay, becomes as short as 108 a second. So you can do the 108 a second time resolve the study. But this is the linear spectroscopy. My sample is there, and using this asynchronous optical sampling, we could measure the free induction decay that could occur in less than 100 femtosecond, right? But still, precisely frequency stabilized optical frequency comb lasers can be used to measure this linear absorption and reflection spectra simultaneously. Well, this is our experimental set. I skipped this one because the more interesting thing is the time resolved the nonlinear spectroscopic application of these dual mode laser system. And we're interested in these kind of chemical and physical and biological processes, and of which time scale varies from femtosecond up to nanosecond. Very wide dynamic range measurement tool is needed, right? And this is schematic representation of our experimental setup. Basically, we have two lasers, and the first time delay tau 1 is actually controlled and scanned by using the translational stage here. But the scanning range is very short, from 0 to 1 picosecond. So we can use this kind of translational stage. That would be better choice. The second coherence time, tau 2, is also controlled by using another translational stage. But the more important waiting time scanning is performed by using the asynchronous optical sampling technique-based scanning method, so that we can actually enjoy the waiting time scan from 0 to a few nanoseconds without any meter long translational stage. That is the important difference between this technique and the conventional two-dimensional electronic spectroscopy technique with just one laser. And this is the low experimental data. It looks very complicated, right? But anyway, this is a three-dimensional data. X-axis is tau 1, y-axis is tau 2. These are two delay times between pulse 1 and pulse 2, and pulse 3 and local oscillator, right? But there is this complicated interference pattern in the time domain. If I take the slice of this entire data at tau 1 equals to 0, it looks like this interference pattern in the time domain. And what is interesting is if you zoom in any part of this interferogram, it contains a series of TW dependent signals at fixed tau 1 and tau 2, right? So again, I like to emphasize that this is the three-dimensional, fully time domain interferogram. So tau 1 and tau 2 are the coherence time. We need to Fourier transform with respect to these two time variables to obtain the two-dimensional electronic spectra, right? So these are four representative two-dimensional electronic spectra from 0 femtosecond up to 2 nanosecond. But actually, we have almost 10,000 or 100,000 of two-dimensional electronic spectra without using very long translational stage. So that is the advantage of this automatic time delay scanning technique based on the asynchronous optical sampling method. And from this high density two-dimensional electronic spectrum, we could extract all kinds of interesting information about the molecular system. And because my time is almost, well over 5-6 minutes, so I'll just skip a few slides. And this is basically the advantage of this technique. But well, no technique is perfect. This technique also have certain disadvantages too. And if time allows, I'll talk about that issue during the question and answer session. So this is the final summary slide. And I talked about the pump-probe study of colloidal quantum dots. And we found very interesting and unexpected ultra-fast Auger process that happens within 1 picosecond. That is totally unexpected. And this work was mainly performed by Dr. Junhyung Lim and Professor Chung and Professor Kwok. The second is a two-dimensional electronic spectroscopy study of a golden nanorod, and we were able to measure the homogeneous diffusion constant, and also nodal line slope analysis provides us very interesting quantitative information about the ultra-fast, again, electron-electron scattering process. The third topic is the surface vibration spectroscopic study of graphene wettability. The hydrogen bond network structure of water on the surface of graphene does depend on the number of graphene layers. So that is a very important lesson we learned from this experimental study. The first topic is novel development of two-dimensional electronic spectroscopy with two synchronized modular lasers. Okay, so that's it. And yeah, these are my collaborators, and I definitely thank them. We would like to have a postdoc application, so you can directly send me email, just in case you're interested in joining us. This project, or there are many different projects in the imaging and microscopy. And this is my team members. That's it. Thank you very much for your attention.
Thank you very much, Min. So I see that there's already questions dropped in the chat.
Yes, I assigned Tono. Tono, go ahead, please. Okay, switch your mic on and ask your question aloud. And then I go to Jürgen.
Thank you very much. And hi, Ming. In the middle of night for you, I believe. I have a question about quantum dots, actually two of them. How were those two electrons put into SE level?
Right. That's basically self-doping process. That means you have to control the relative number of mercury and sulfur atoms precisely. And the passivation layer plays a very important role to stabilize such a quantum dot. So that's a special technique. And I'm very glad to have a collaboration with Dr. Chung. Do you want to see the slide or?
Well, that basically answered, because I was guessing something along those lines. And then I have a question about this very super fast Auger, because the interband Auger is like 2 orders of magnitude slower. Do you understand why is it so fast?
Well,
what you see?
as far that's a very good question. Actually, that is the reason why it took a very long time for us to finally make ourselves comfortable with this conclusion. Typical the interband or band gap Auger process occurs in tens of picoseconds, much slower than 1 picosecond. On the other hand, here we definitely observed 1 picosecond decaying component in our pump probe signal, quick drop right there. So this is experimental fact, and there is no question about the validity of this experiment itself. But the interesting clue was found by carefully examining the electron density of 1SE state and 1PE state. This 1SE state, you cannot see the electron distribution of from this figure, but essentially all the electrons are delocalized on the surface of this colloidal quantum dot. The core is more or less empty when the electron occupies 1SE state. And likewise, 1PE states, they also have delocalized electrons on the surface. So that means these two wave functions are spatially well overlapped. So I guess that is why they can sort of strongly couple to each other. But if you are interested in band gap conventional transition, then you have to consider these two electron densities, 1SH and 1SE. They do not have that strong spatial overlap. So I guess this is probably one very important clue. So without the ab initio calculations of these orbitals, then, well, we cannot make any sound conclusion from these experimental studies. But after we took a look at this computation results, we are pretty happy and excited.
Thank you very much.
Okay, Jürgen, please unmute your mic and go ahead with your question.
Hello, thank you for your talk. Oh, I can even share my video. Yeah, here I am. Hi. I have a quick question on your nanorod data. So you show super fast components, something like 50 frames per second, and then followed by 5 picoseconds. I was wondering, did you include any pulse overlap effects in your analysis? Because when I look at your data there in A, then this perfectly looks like double quantum coherence data, for example, no? And this would heavily distort your nodal lines, of course. Thank you.
That's true. So this is actually time-resolved two-dimensional electronic spectra. If you look at this, then apparently you can immediately identify there is a kind of scattering pattern that will obscure the two-dimensional electronic spectra, right? So at very short time and or even negative time, we could see the ripples here. And this is another headache. And it took a long time to figure out and rationalize this kind of experimental observation by taking into account another nonlinear optical process. That is something like this. So we have this is the normal geometry. Pump 1 interacts with the sample first, and then followed by pump 2 and probe beam, you detect the spectrum, right? That's the conventional and very normal and easy to understand measurement. But if the delay time is negative, or I call it reverse time ordering, then probe field precedes first, interacts with the sample, and then followed by pump 1. And these two pulses propagate non-collinearly, right? So these two pulses will create transient grating within the sample. And that transient grating will scatter the pump 2. So although the normal pump 2 will propagate following this red line like that, it does not go to detector. It should not normally. But because of the transient grading created by a pair of pulses, probe and pump 1, this pump 2 will be diffracted by the transient grading, and then that diffracted pump 2 interacts with the signal. So there is a time varying interference that actually occurs and that is observed in this two-dimensional electronic spectra at very short time and even negative time. That is why we intentionally ignore the really short time part here. I mean, these data points, we do not put any meaning. That's why we just ignore the short time part. So only after 150 femtosecond, when the pulses are not completely overlapped, the pulse overlap is relatively minimal, then we just took into account the data points after that. So this is sort of a transient change of the nodal line slope. And that is probably associated with the really fast the electron heating process. And that was the conclusion. But we could not actually quantitatively analyze the entire two-dimensional spectra by just simply looking at these spectra. Some of them looks very complicated because of the ripples or the scattering signals. Only when you extract the nodal line slope from these complicated two-dimensional spectra, then you can see very well-behaved, nicely changing data points in time.
Okay, Donatas sent me a message that he kind of waived his question. Okay, so then we go to the next question, quite interesting. Miriam, please unmute and ask.
Yes, thanks, Ben, for the talk. I'm a graduate student in Marty Zanni's group in Wisconsin. So my question is, I think I might be missing something with the motivation for the 2D electronic spectroscopy with frequency combs. I usually think of the motivation for using frequency combs to get like super good frequency resolution, but I see you're doing it in the condensed phase, which I don't remember reading other papers with people doing it in the condensed phase, so I think that's cool. But then your line width is so much larger. Is that increased frequency resolution, is that helpful then with those larger line widths?
That is actually a good question. You know, the frequency comb technology itself was developed by a group of people who were interested in precision measurement. They want to measure frequency very precisely. So controlling the carrier envelope offset frequency and do I have a slide somewhere? And the repetition frequency, you don't have to use any kind of calibration process to measure or estimate the unknown frequency, basically, because that spectrum of the comb laser itself is an exceptionally precise ruler. So in that case, of course, you can enjoy the high precision and frequency stabilized comb laser. And however, the typical absorption spectrum of a typical dye molecule or some biological systems and even functional materials, the spectrum itself is very broad, and you don't need to have that high precision frequency tool at all, right? So in that sense, the dual frequency comb technique was initially used specifically to study the gas phase molecular system. They could measure the raw vibrational spectrum precisely without worrying about the calibration process afterward. So that is wonderful. But as a chemist, or more specifically physical chemist, I'm definitely interested in utilizing this kind of technique to study ultra-fast phenomena, nonlinear optical process, and condensed matter system, right? So I give up to use a high frequency resolution capability of optical frequency comb. I just adopted this kind of asynchronous optical sampling technique so that we can achieve very long waiting time scanning. The dynamic range of waiting time scanning covers almost the 6 decades. That means from femtosecond up to nanosecond. With the femtosecond time resolvability, we can enjoy this technique, right? So in a sense, my direction is slightly different from the dual frequency comb researchers who are interested in utilizing, maximally utilizing the high frequency resolution. So I guess that answers to your question. If not, you can just send me an email after this.
Thank you so much.
Okay, thank you. I think that in view of time, we should move to Kevin. Okay, take over, yes.